Okay, in part 2 of chapter 5, we are going to look at the moon. The moon is unique in that it's, in relation to its host planet, it is the largest moon in the solar system as a fraction of the mass of the host planet. And in some cases, some people regard the Earth-Moon system as a double planet. Not too many people, though. Our moon is the second brightest object in the sky after the sun, so it's definitely noticeable. Many primitive and modern societies base their religious ceremonies on the cycles of the moon, especially the new and full moons. And our month is based on the moon cycle. It is viewed that the year is harder to keep track of, since 365 days in a year. It's just hard to know exactly when the same day appears 1 year apart. But with the moon cycle, approximately a month for every cycle, it's much easier to keep track of that, and especially with the phases of the moon, you can keep track of time a little bit better. So the moon is inherently intermixed with our calendar. Radius of the moon is 1,700 kilometers, 27% of the radius of the Earth, so just approximately 1/4 of the radius of the Earth. Mass is 1.2% of the Earth's, so the moon is about 1/80th the mass of the Earth. Density is 3.3 grams per cubic centimeter. Pure water, by definition, is 1 gram per cubic centimeter, so it's about 3.3 times the density of water. Earth is about 5.5 times, so this density is only about 60% the density of Earth. Distance to the moon is 384,000 kilometers from Earth, about 250,000 miles, about 250,000 miles, about as far as my old car has driven in its lifetime, about 250,000 miles. So I could have driven to the moon. July 20th, 1969 was the day that human beings first stepped on the moon. Neil Armstrong was the first astronaut on the moon. And what were the first words spoken? Do you happen to know the first words spoken when Neil Armstrong stepped on the moon? It was, "Oops, did I remember my boots?" No, it was, that's one small step for a man, a giant leap for mankind. Looking in the visor, you can see the reflection. This particular picture, you can see the other astronaut, Ed Aldrin, and the lunar module. So when you're looking at the moonscape, nothing much there. Well, how do we know that we actually were on the moon? Well, if someone doesn't believe you, the definite proof is the fact that you can send a laser up to the moon and it will reflect back if you hit it right on one of the retroreflectors left by the astronauts there. So in other words, if those retroreflectors weren't left there by the astronauts, you wouldn't get your laser back. And so that's proof that we've been there, if anybody were to doubt that. This retroreflector sends laser beams right back to the origin. It's going to spread out a bit over the course of its travel. It uses 100 corner cube reflectors, measures the rate of continental drift on the Earth because it's precise, allows for changes in the Earth's tilt, can calculate the distance to the moon, how that's changing, and it turns out with this measurement that the distance to the moon is increasing by 3.8 centimeters per year, about 1.5 inches. And it can help establish the gravitational constant the gravitation between the Earth and the Moon and measure that, and has found that that constant is steady to 1 part in a billion. Here's a look at the Moon, a sight that you could probably see through a basic telescope. And in fact, when Galileo first looked at the Moon, he probably saw something like this, and realized, and being the first human being to do so, that the Moon had a three-dimensional aspect to it. You know, if you look out on any particular night using the naked eye, you see a two-dimensional white object. But you look at it through a telescope, you see that it's definitely spherical. It's a three-dimensional heavenly body, and that gives you a new perspective on the universe when you see that here's an object, another world, just like the Earth, another world existing out there. Composition history of the Moon. Well, it's obviously we know that the Moon is made out of cheese. No, it's not made out of cheese. We actually know more about the composition of the Moon since the first lunar landing on July 20th, 1969. There have been 5 other lunar landings: Apollo 12, 14, 15, 16, and 17. Of course, Apollo 13 was the one which had an explosion en route, and so the main thrust of that mission was to try to get the astronauts back safely, and they did. The other Apollos landed on the Moon. The Apollo program was cut short after 17 due to lack of funding. The Apollo missions brought back 379 kilograms of lunar material, over 800 pounds, brought back to Earth. And using radiometric dating techniques, which involves up to between 6 and 8 different isotope techniques, not carbon dating, but radiometric dating, has found that the mountain rocks on the Moon are between 3.9 to 4.4 billion years old, and the rocks in the plains, the darker areas that you see when you look at the Moon, are between 3.1 and 3.9 billion years old. No rocks found by these astronauts on these missions were found to be older than 4.4 billion years old or younger than 3.1 billion years old. So it's thought that no other new rocks have been formed since 3.1 billion years ago, which gives you some indication that maybe the volcanic activity on the Moon stopped 3.1 billion years ago. Here's a look at the near side of the Moon and the Apollo landing sites. Apollo 11, 12, 14, 15, 16, and 17. Here's some of the rocks brought back from the Moon. Anorthosite, a feldspar, a common type rock on the Earth, a little bit purer on the Moon since you don't have as many of the impurities in this rock. Breccia, angled rock formed when due to impacts, so a lot of lunar impacts have formed this conglomerate of rock. Basalt from the Marias, we can see it looks very similar to volcanic basalt that we would find on Earth. And regolith is here's a microscopic view of the soil of the Moon, and very minute soil, basically comprised of volcanic type material as well. Here are the 3 astronauts of Apollo 11, and being the first on the Moon, at least Buzz Aldrin, I said Ed Aldrin, Buzz Aldrin, and Neil Armstrong were the first 2 human beings on the Moon. Michael Collins flew the command module around the Moon, waiting for them to come back. But being the first 3 astronauts on the Moon and discovering what appeared to be a new rock at that time, they got their name on that rock. So Armalcolite is a rock that looks like this. But actually this kind of rock can be found on the Earth, so it is called Armalcolite. This kind of looks, this particular sample actually is an Earth sample, and it kind of looks like a arrowhead. But it was named after the 3 astronauts, Armstrong, Aldrin, and Collins. So they're pretty happy about that. Actually, this picture, why they're happy, was because after being on this mission, they were happy to see their wives again. If we were to compare the moon and the Earth, we'd find that the moon is much smaller. It'd take about 4 moons to expand the diameter of the Earth. So the moon is 1/4 the diameter. The moon is 1/80th the mass, and the mitigating factors of being smaller and being so much less mass means that the gravity on the moon is only 1/6 the gravity of the Earth. The moon is 60% the density of the Earth, which suggests that its mode of formation might be different from that of the Earth. So if you travel to the moon, you would weigh, if you weighed 180 pounds on the Earth, you would weigh 30 pounds on the moon. If you still retained your Earth muscles, then you'd feel kind of powerful on the moon, at least for a little while. Here's the Earth and the moon. As we said, the moon compared in size to the Earth, even though it's 1/4 the diameter, as moons go, that's pretty large in comparison to its host planet. And like I said, some astronomers might even actually call it a double planet, but not too many. And but if you actually consider the Earth-Moon distance, it would be more like this. In other words, it would take a bunch of Earths to fit between the Earth and the Moon, and they're actually quite far apart. There's 30 Earth diameters between the Earth and the Moon, which would translate into about 10 times the Earth's circumference. So if you peel the Earth, look at this circumference, 10 of those would make it to the Moon, because the Earth is 25,000 miles around and it's 250,000 miles to the Moon. 250,000 miles. So it's 500,000 miles there and back again. 2 trips to the Moon is 1,000,000 miles there and back again. Gravity is what holds things to the Earth, at least to the surface of the Earth, and gravity is what holds the Moon to the Earth as well. The Moon's rotation and revolution are tidally fixed by the Earth. Earth's tidal influence also caused the Moon's maria, or seas. In other words, when the Moon had a more molten interior, part of that interior was pulled out on the side of where the Earth was due to its gravity, and caused the lava flows that we see on the surface of the Moon. The dark areas on the near side of the Moon are the maria, or lava flows, also called the seas. The Moon's tidal influence is mainly on the Earth's oceans. So the Moon has the influence on the Earth's oceans. The Earth has the influence on the Moon's seas, which were actually seas of lava. But the Earth also has a tidal influence in keeping the same side of the Moon fixed towards us at all times. So the Moon rotates on its axis at the same rate it revolves because it's fixed, showing us the same face, one side of the Moon, all the time. So as it's revolving, it's keeping that face. Hence, the Moon will go once around in relation to the Sun. It'll take 1 month for the Moon to turn once around in relation to the distant Sun. So the Moon day is 1 revolution around the Earth, 29.5 Earth days long. since the moon is always facing the Earth, at least the near side of the moon is always facing the Earth, if you were on the moon and you're facing the Earth and you could see the Earth in your sky, then you would always see the Earth in your sky, because your side would always be turning towards the Earth all the time. And so if you're on that half of the moon that sees the Earth, you would always see the Earth. And if you're on the other half of the moon that did not see the Earth, you would never see the Earth. This is a famous picture here taken by Apollo 8, which did not land on the moon, but it was a mission to carry out a revolution around the moon. And this picture was taken in Christmas 1968, and it's one of my favorite astronomical pictures, showing the surface of the moon and the Earth in the background. Daytime on the moon lasts 14.75 Earth days. Nighttime lasts 14.75 Earth days. So a day is almost 15 Earth days. And it gets quite hot, so the lunar missions were always scheduled near sunset or sunrise on the moon, so that the insult that 14.75 Earth day, lunar day. Moon surface features were formed millions of years ago, actually billions of years ago, and there's no erosive forces other than micrometeorites hitting the surface and destroying things that way. But other than that, there's no erosion, there's no wind, there's no water, so it does not erode, and there's no organisms to break things down. So what you've got is a snapshot of history as it was billions of years ago, a preserved record of the past, and hence a study of the moon would be incredible if we could go there on a regular basis to study the history of the solar system from billions of years past. The moon's albedo is only 7%, so it appears bright in our sky, but the Earth in comparison is 35%, 5 times more. So the Earth in the moon sky is incredibly bright, and the Earth is bigger to begin with. So in relation to that, the moon is relatively dull, but it still appears quite bright in our sky. Albedo is the amount of light it reflects. General composition of the moon. Moon has a core, mantle, and crust. All of them are thought to be solid. The crust is thicker on one side, actually the far side. Presently, the moon does not have a magnetic field, so there's no dynamo effect. The moon's spin is very slow. It rotates once in 29.5 days. The moon has less iron than the Earth. The rocks brought back show some magnetism, indicating that the moon had a slight magnetic field at one time. So it was spinning maybe, or had molten material at one time as those rocks were crystallizing, but not now. If we look in the moon's interior, we have the maria made out of basalt material, solid. We have the crust and mantle material made out of the same similar materials as our Earth's crust and mantle. So it's made out of rocky silicates similar to the Earth's crust and mantle. Far side is a thicker crust, about twice as thick as the near side, and the molten basalt seems to be pulled out, most likely due to the Earth's tidal pull on the near side. So you see the seas, the marias on the near side, and you see less of that. I think there's just one relatively large maria on the far side, and it's mostly just craters. A lot of that thickness then is just the fact that the the molten material has been pulled to our side, and also the far side is going to be pelted more by meteorites from outer space, because the near side is going to be protected in a sense by the Earth's presence. The Earth would have gotten hit by more of those on the near side, and the far side is going to be hit more, and hence a lot of that material that hits the moon is going to collect there, and so you're going to have more of this dusty, rocky material from meteorite impacts on the far side of the moon. And we'll see a picture of this evidence a little bit later. Well, we'll see it right here. Here's a picture showing the near far side line of Apollo 16, and so it's a division between the near and far side of the moon. And we see on the near side we can see these marias. You can see smaller craters here, or just less amount of craters, and on the far side it's just heavily cratered, as it has not covered up. Marias did not flow, and it's got much more impacts on the far side. Quite a difference between this line. Here's a man on the moon, and of course, as everybody knows, we actually didn't go to the moon. I mean, this is actually a sound stage in Hollywood, possibly. In fact, this picture was taken, if we show the true picture undoctored, we can see that this was taken at the Space and Rocket Center in Huntsville, because we can see these tourists in the background, and we can see the shuttle. So, I'm just kidding. We actually did go to the moon. This is the actual picture on the moon with footsteps and horizon and everything else in the lunar lander. Here's an astronaut on the moon. Some people say, well, there can't be any wind on the moon, so why is this flag showing wind? Isn't that evidence that we didn't go to the moon? And of course, this flag was intended to look like it had wind, so it had a wire backing, so you can bend that, and when you shook it, it would shake it as well. So it's just made to look like there's wind, but there is no wind on the moon, and no weather on the moon either. There's no atmosphere to have weather, and there's no water to have weather patterns. Looking at this famous photograph, I'm reminded of a cartoon. Looks like this, with the astronaut on the moon and the flag. He's reading a note. If we look in closer, it goes like this: Dear Henry, where were you? We waited and waited, but we finally decided that maybe you got another ride back to Earth, or maybe you liked it so much here you want to stay a little bit longer. Who knows? The far side. But that's a good segue to look at the far side of the moon. This is the far side of the moon, the side that you can't see, but it's not really the dark side of the moon, because it gets as much light as the near side of the moon. It goes through that same lunar day, 14.75 daylight hours and 14.75 nighttime hours. But this is the far side of the moon that you can't see, the back side of the moon. So it's not always dark. It's more cratered and thicker with less Maria. You can see a little Maria right there and a little Maria over here. First seen by the Russian Luna probe in the late 1950s. In fact, all the major features on the far side of the moon are named after have Russian names. So they got the credit for actually sending a probe around the moon. They get credit for naming all the features. Here's a look at the moon on the near side. The Mercator, you can see the Maria on the near side, and the Tycho Crater down here. if we were to take the surface of the moon and stretch it out like we do often with the Earth, or we take the spherical Earth and we put it on a flat map, if we did the same thing with the moon, stretch this out, we would see a map that looks like this. You can see all the Maria bunched together here in the middle, and then you see the far side, and so it's just that one area where there was a lot of lava flows. Latest thinking from Ohio State University in 2006 is that maybe an asteroid hit the far side of the moon, and that helped jiggle the interior of the moon to the near side and cause a shift of the core and Maria to occur on the near side. But that's not necessary since we got the Earth's gravitational pull as well, and that can explain the Maria as well. Well, there's craters on the moon, and the large craters were formed by meteoric impact between 4.1 and 4.6 billion years ago. The larger craters are older. They indicate a time in the solar system when large bodies were flying around in the solar system in mass and bombarding the Earth, the moon, all the planets, or getting hit by large objects early in the solar system, 4.1 to 4.6 billion years ago. As the crater size gets smaller, that indicates the objects hitting on the average were smaller, and that indicates lesser time ago, newer craters. And in fact, you can see the large craters with newer craters inside them, which definitely indicates that these are younger than the large craters because they're actually impacting inside the feature of the larger crater. So the crater count is a measure of age in a sense. As you look at how many craters you have and what their sizes are and so forth, and counting them, you could figure out in essence the age of different areas in the solar system, and you can apply that to the moon. If you have a meteoric impact, meteor comes in with a lot of energy, hits the surface, there's an explosion as it moves material outward called ejecta, and that ejecta will possibly, most of it will come back to, in this case, to the lunar surface. Some of it will be thrown outward and actually into space and possibly land on the Earth. But a lot of it will come back, and you end up with a crater with a rim and a pulverized crust, and maybe something left over from the meteoroid, and now a meteorite. But most of that material thrust out from this crater is now in the rim of the crater itself. So if you took all that material, thrust down the rim, and filled it into the bowl, then you would retain the surface of the moon. So there's not material lost here. A lot of the mountains on the moon are formed in this way from meteoric impacts. As they push material up on one side, you get mountain ranges on that rim. Here's a very large meteoric impact on the moon, the largest one on the moon. Orientalia Crater, which is at the south pole of the moon, so you can't see it. But you can see evidence of 2 and possibly 3 rings on this crater. So it has had an impact and a reverse response and an impact again, and molten material. It looks like spaghetti sauce. If you drop something into spaghetti sauce, you would see this kind of plop double impact here. Here's another look at the Orientalia Basin. And some people have put forth the notion that if this were the side of the moon that we are looking at, then a lot of our mythology over the ages would be a whole lot different, because this side of the moon kind of looks like an eye. kind of looking at the pupil of the eye, and the eye is looking down at you. So the moon is looking down on you, if this were the side of the moon looking at you. Waiting for that eye to blink. I guess it won't blink. The dark basalt were formed by volcanic activity at about 3.9 billion years ago. Hence, the youngest craters reside in the Marias. So you had the larger craters, and after a while you have the lava flows, and then if there are craters after that, then they have to be younger craters, younger impacts. Galileo thought the Maria were seas of water, and hence that's why we ended up with calling these seas, or Marias. And he thought the craters themselves were volcanic calderas. Now, what's left after a volcano has blown its top, you have the caldera. So he thought those were calderas, and hence all these features were misnamed from that tradition. Why are the Marias black in color? I mean, of course, they're made out of volcanic material, which could be black as well. But if you looked at this material, as we saw in the basalt sample earlier in this lecture, it's not necessarily dark black like we see it here. And the reason it appears black to us is because, in a reflective sense, it's more specular. By specular, we mean that when light hits it, it's more mirror-like. So it's going to bounce off and continue on, and hence less of that light is actually going to come back to you. And if light doesn't come back to you, then you're not seeing that light. It appears dark. So if you had a mirror and you have an image and it reflects off that mirror, it will appear dark from that angle. And hence, like a mirror, the Marias appear dark to us. In contrast, the more diffuse areas, like the area around Tycho Crater right here, which has more rocky and so when light hits it, it reflects light in all directions. Hence, a lot of that light does make it back to you. So that area appears lighter in color than, say, the more smoother Maria, the more specular Maria. Here's a look at the largest Maria on the moon here, Maria Imbrium. Closer look at it. And this corner over here was where one of the Apollo missions landed. And in fact, right there in that area was where Apollo 15 decided to land. Always a challenge. You can decide where you want to land, but when you actually get down there, there may not be as smooth an area as you think to land. So the pilot has to kind of fly around a bit to figure out exactly where they can land. Here's the Tycho Crater. It's one of the more visible craters on the near side of the moon. A very bright white crater in contrast to the darker Maria. And it's named after Tycho Brahe, the famous astronomer back in the 16th century. Closer look at the Tycho Crater, and you can see a more diffuse reflection, making it appear lighter in color. Here's a look at the loose debris on the surface of the moon, which can be very fine, but volcanic in origin. You can see how some of it melted into these little balls. It's called regolith, and a lot of these pieces are from impacts as well, just these micrometeorite impacts creating smaller pieces. And you have this real fine regolith type sand, similar to volcanic rock on the Earth. Any theory of the origin of the moon must take into account certain facts. The lunar rocks are similar to the Earth's mantle, the same kind of material as the Earth's mantle. Why is that? Why don't we have more diversity in the rocks? Why aren't they similar to the different kinds of rocks that we see on the Earth, iron and denser material? Why is it similar to the Earth's mantle material? Oxygen isotope ratios indicate that the Earth and the Moon were formed at a similar distance from the Sun. So that's interesting that that they have a similar distance. They didn't come from somewhere else, most likely. There is no water in the lunar rocks that have been found, even though there's been discovered water on the Moon. There's a deficiency of volatile elements, thought to be driven off by heat. So you have pure quantities of what's left, but the instigating elements that might be slipping in there into those rocks are not there. Relative to the Earth, the Moon has less iron. Density of the Earth is 3.3 grams per cubic centimeter, while the Earth is 5.5 grams per cubic centimeter on the average. So the Moon is only 60% the density of the Earth. And the oldest rocks on the Earth and the Moon are similar. So it indicates a similar age to the Moon. Well, the most widely accepted theory to date is called the Great Impact Theory. I like to call it the collision theory, just to give it a C and a shorter name. It's the Great Impact Theory or collision theory. In this theory, a planet-sized object, probably about the size of Mars, struck the Earth with a glancing blow 4.4 billion years ago, resulting in the ejection of matter into orbit to form the Moon. Now the thought is that this planet-sized object probably coalesced with the Earth in the same general area. So it didn't come from somewhere else necessarily. It was basically in the same orbit as the Earth, and the Earth probably was smaller at that time, maybe about 90% of what it is now. And so the Earth took some of this material from this collision to make it bigger itself, and what was left formed the Moon. Maybe looking something like this. There's an actual picture taken from that impact at that time. In this collision theory, the colliding body would be in the ecliptic plane. The lighter material would be driven off by heat. That would explain the loss of the volatile materials. And the fragments would then coalesce into the Moon. And you would also not have the iron, because if it were a glancing blow, then you would just get material from the mantle. So hence the Earth would kind of steal the heavier material, and the lighter material, the mantle material, would coalesce eventually into the Moon. And so the Moon would actually form at some distance away from the Earth. Here's some other theories. Maybe the Earth captured the Moon by gravity. This has some drawbacks. This would not explain why the Moon is near the ecliptic plane, because if there were capture, it could happen at any orientation. And it's unlikely for a body as big as the Moon and as far away as the Moon is for the Earth to have enough gravity to capture it. The Earth has enough gravity just to hold it barely into orbit, and to have something as big as the Moon would have a lot of momentum, so it's very unlikely that the Earth could capture such a body. The co-formation theory, the Moon formed out of leftovers. This would explain why the Moon has a prograde revolution around the Earth, like the Earth does around the Sun, and all the rotation of the Earth, the Sun, and most of the planets. So it would be consistent with the solar nebula theory. But if so, then it would be expected that the Moon should revolve around Earth's equator if it were co-forming with the Earth out of leftovers from the Earth. And it's not around Earth's equator. It's closer to the ecliptic. The Earth is tilted 23.5 degrees. Now, possibly, if you really want to keep this theory, it's possible that after the formation of the Moon and the Earth got hit by something else, which moved it off kilter. Well, we have a probe out there, the Smart 1 moon probe. It's powered by a very weak engine, a xenon ion engine. It's the Smart 1 probe. But it's making its way to the moon. It's been launched, and it's going through these ellipse orbits, gradually gaining distance from the Earth. And its mission is to actually look for evidence of this possible collision between the Earth and this Mars-sized object. Because if that actually happened, there should be remnants of that collision still in the Earth-Moon plane. So Smart 1 is looking for that, investigating this collision theory. There's no hydrosphere, no water due to the weak gravity of the moon and the hot daytime temperatures. Recently, there's definitely been discovered a lot of water on the moon in the crevices of craters that are near the poles that never receive sunlight. So at one time, maybe the moon was bombarded by water-like objects like comets, just like the Earth has been theorized to have been bombarded by such things. And most of that went away because of the moon's weak gravity and the heat of the day and no atmosphere. However, what hit inside the craters would be retained if it never receives any solar energy. So what water is on the moon has been detected in the shadows of the craters at its poles. Here's the lunar module on its way to the moon, and you can see the Earth in the background. You know, the people who took these pictures, the camera crew that went along, they really don't get much credit for their travels to the moon. It's you got the astronauts that get all the glory, but the people who actually went with them and took the pictures, they were astronauts too. Now, this picture was taken by the command module, so Michael Collins on the command module. So that's there was no photo group there. Moon lacks an atmosphere. The gravity is too weak. The daytime temperature too hot. Here's a look at the phases of the moon. Here's the moon with all the mareas, the different seas of lava flows. And this effect of light and darkness on the moon kind of gives the effect of a face on the moon. You have to use your own imagination to figure out where that face is. But if you want help, I'm going to give you help. So as we look at this moon and try to find the man in the moon, we might recognize a mouth somewhere down here, and maybe an eye up here, and another eye over here, and maybe a nose right over here. So there's the man on the moon, and then an ear over here. It's one way to look at the man on the moon. Kind of looks like Arnold Schwarzenegger in Terminator. Now, it doesn't look like Arnold Schwarzenegger in Terminator at all, but it allows me to do a segue to the next item, which is the Terminator. The Terminator is a line between darkness and light that occurs on heavenly objects, including the moon. Daytime temperature in the moon rises to 400 degrees Kelvin, which is about 260 degrees Fahrenheit. That's above the boiling temperature of water, so you could cook things in the daytime pretty easily on the moon. Nighttime falls to 100 degrees Kelvin, which is about minus 280 degrees Fahrenheit, so you could definitely freeze things on the moon. In fact, that's pretty close to liquid nitrogen temperature. Here's the moon, and we just saw the man in the moon. And not to spend too much time on this, but can you see the dog in the moon? He's looking at the near side of the moon, and you recognize a dog in that picture. Need some help? There you go. Okay. Maybe a little bit too much imagination. There is no life on the moon except for that indicated here. In other words, it looks like there at one time was life on the moon, at least on July 20th, 1969, with these footprints. And these footprints are well preserved because of lack of erosion. There's no water on the moon, so you wonder how can they make footprints like that. But it's actually a problem for a lot of the equipment that they have to have all this dust, fine dust, get into mechanical equipment. This is kind of neat that you can see footprints on the moon that's well preserved, and nothing's going to change that. So in the future, if you want to take a vacation to the moon and see where astronauts first landed on the moon, you could go there, and this probably be cordoned off, and go to the point where the astronauts first were on the moon and still see the footprints and equipment of those astronauts still left there, preserved for a very long time. This picture makes it appear like there might be birds on the moon. Of course, that's just an optical effect of birds being in our atmosphere. Lunar module on the moon, left there. Some neat pictures showing the surface of the moon and the horizon here. Beautiful landscape. When Buzz Aldrin called it beautiful desolation. You can see the lunar module. You can see how the sand is just kind of clings to everything. And possibly that could be a danger, because if you have equipment, mechanical equipment, and that dust is getting into it, it could alter its operation. Look, this is Apollo 15. Got pretty far away from the lunar module over there. Having some fun, I guess, riding the dune buggy. Here's a return to the command module. We're just traveling around the moon. It'd be hard to be that third astronaut who doesn't get the chance to go down and step on the moon. Tidal forces. Tidal forces are related to gravity. It's a gravitational force, but it depends on how close you are to that gravitational force. So it depends on its gradient. And because of the closeness of the moon to the Earth, the moon has a great force, a tidal force, on the oceans, and it's differential. So that means the water that's closest to the moon is going to get more of a pull than the water that's further away. And hence the water that's on the other side of the Earth is going to be getting the less possible pull. So you're going to end up with two bulges on the Earth as far as its ocean. The sun's gravity is greater than the moon's, but because of the location of the moon's tidal force is twice that of the sun, or the sun's is only 1/2 the tidal force of the moon. And the near side is pulled harder than the far side, allowing these two bulges in the ocean to occur. The Earth exerts a strong tidal force on the moon, at one time helping to create the moon's maria, the seas of lava flows. Another effect of the Earth's tidal force is the fact that the moon is always showing us the same side all the time. So the fact that the moon is tidally fixed to show us the same face all the time is a great effect of the Earth's tidal force on the moon. Moon exerts a tidal force on the Earth, affecting our tides, affecting the water on the Earth more easily than the land because it's movable. And the water on the opposite side is pulled less than the water on the near side, hence we have 2 tides every day, 2 high tides and 2 low tides every day due to this effect of the moon's pull. There's a tidal offset to the actual location of the moon because of the Earth's centrifugal force if we're in the Earth's frame of reference. So because of the spin of the Earth, there's a momentum to the water, and hence even though the moon is pulling it outward, we don't really reach high tide until the moon is past that point by about 1 or 2 hours. So there's a little offset. So you couldn't say high tide and then directly see the moon there. The moon would be a little bit offset at that point. Spring tides occur when the sun and the moon act together in order to create higher tides and lower tides than usual. So if the moon and the sun were on the same line, either at the moon being at a new moon or a full moon, on the same line of action, then their forces work together and create spring tides. Neap tides occur when the 2 forces are opposing each other. The sun is pulling one way, but the moon's pulling the other way, and hence it kind of mitigates the effect of having a high tide or a low tide, for that matter. So at first and third quarter moons, when the moon and the sun are at right angles to the Earth, they will mitigate each other's effect, and hence you'll have a neap tide. Neap tides, the moon's tidal force is counteracted somewhat by the sun's tidal force. Consequences of the tidal forces: the Earth's spin is slowing down, and hence if the Earth is slowing down its spin, it's going to take longer to complete a day, and in fact the length of a day increases by 0.002 of a second every century. Earth precesses on its axis like a top due to the moon's, and the moon helps to keep that in order, so that the fact that we have a stable seasonal action is largely in part to the moon, and that's a good thing. So a lot of our advantages in having a stable climate is due to the action, the gyroscopic action of the moon. Moon is moving away from the Earth at 1.5 inches per year. And the moon's synchronous orbit is a result of the Earth's tidal pull on the moon. So the moon always showing us the same face, rotating and revolving at the same rate, is a tidal force of the Earth on the moon. And we'll see this occur definitely with the larger planets on their smaller moons. Their smaller moons will be tidally fixed to the larger planets. That concludes the second lecture of Chapter 5.